So problem number 1 from our second exam has a book of mass M sitting at rest on a table, and there's friction between the book and the table, and you're trying to get the book moving, overcoming static friction by pushing on it with a force of magnitude P at some angle theta above horizontal. Part A says to draw the free body diagram or force diagram and coordinate system for the system. So I've already got the pushing force on there, P. So let's continue. We've got gravity pulling down with a force mg. We've got the table pushing up on the book with a normal force N. That's a contact force, although not friction between the two of them. The other contact force is the force of friction. That's resisting movement of the book, so it must be pushing to the right, and we'll label that F sub F for the force of friction. Okay. You also have to add a coordinate system, and you have only one reasonable option, which is horizontal and vertical axes, but you can put positive x to the right or to the left. I'll just pick it to the right, but that's arbitrary. It's not really important. So there are 4 forces, mgn, the force of friction P. This is my free body diagram and my coordinate system, so that's done with part A. Part B says, what's the minimum force P, pushing force, required to get the block moving? Okay. That minimum P will correspond to the maximum force of static friction that you have to overcome, and that force of static friction max, I'll just remind you, is equal to mu s times the normal force. Remember, at any given time, if you're pushing with less force P, you'll have less force of friction resisting it, because the sums of the forces in the x direction have to be 0 if the book isn't moving. It's because it's then certainly not accelerating. And so in general, the force of static friction is less than or equal to mu Sn. Okay, but we'll just set equal to mu Sn because we're interested in the maximum force of static friction, and therefore the minimum pushing force you need. Okay. So in any case, to find the force of static friction means we need to find the normal force, and you find the normal force by looking at the sums of the forces. And what just happened to my pen? The sums of the forces, sorry, it stopped working for a moment. The sums of the forces in the y direction will be equal to, now I just look at my free body diagram and I say, well, I've got a normal force in the positive direction, and I've got a force of gravity pointing down in the negative y direction. And I have a component of the pushing force. Notice that the pushing force looks like this. Then you have a vertical component, P sine theta, and a horizontal component, P cosine theta. And so I need to take into account minus P sine theta, because it's in the negative y direction, and those have to sum to 0. And I can solve this for my normal force. The normal force equals mg plus P sine theta. Okay. Now that I've got the normal force, I can find the maximum force of static friction, and I can move on to the sums of the forces in the x direction. And just look at my diagram. I've got a component of the pushing force in my negative x direction, minus P cosine theta. I've got a force of friction in my positive x direction. That's mu s times the normal force. We already know the normal force is mg plus P sine theta. And those sum to 0 if the book isn't moving or isn't quite moving. Now this equation, since we're after P as a function of all the other terms, I look at this and I see, well, I can just isolate P on one side of my equation. So let's just do that on the left side. So I have a P, I have a mu s sine theta, and a minus cosine theta here. And the other side of the equation will then have a minus mu s mg. And I can just write down the answer for the pushing force P that I want. Now notice I have a minus mu s mg here, so I'm going to convert that to a plus mu s mg, and I can do that as long as I flip the signs of this next term and write this as cosine theta minus mu s sine theta. Now, these are just some choices in algebra. They're reasonable, but you could make other choices in how to show this. Okay. In any case, I have my minimum force P necessary to get this thing moving. Now, there's an optional part of this problem that says, why don't you do a quick check of your answer? If theta equals 0, it's not required, remember, but if theta equals 0 degrees, that means a horizontal push, which means the normal force equals mg. We see from my answer above that theta equals 0, well, cosine theta just becomes 1, sine theta becomes 0, so my answer just becomes mu s mg. But that should make some sense to you, because if you're pushing with a horizontal pushing force, then the normal force is mg, and the maximum force of static friction, mu s n, is mu s mg. So this checks out. My answer is, I'm reassured that my answer is right. So now let's move on to part C. Part C asks if there's a critical angle for the pushing force, so that if you try to push at the angle, you cannot get the block moving. Well, just look at your result for P, and you'll see that, well, if cosine theta is small, then this first term, cosine theta, is going to be bigger than the second term, and you'll have a positive value. But what happens if cosine theta minus mu s sine theta is 0? Well, in that case, you need an infinite. You have a P equals mu s mg over 0, which means you need an infinite force, which you cannot do, which means you cannot get the block moving. In fact, if you go to even steeper angles, then cosine keeps getting smaller, sine theta keeps getting bigger, and you'll need a negative pushing force, which makes no sense. Okay, so what we see is that when this condition, cosine theta minus mu sine theta equals 0, something dramatically has changed about the physics of the problem. Well, what is that theta? Well, we can solve for that. Let's just write this as sine theta, okay, mu s, okay, equals cosine theta, just taking that to the other side, or sine theta divided by cosine theta equals 1 over mu s, or theta, which we'll call theta critical, is the arc whose tangent is 1 over mu s. So given the static coefficient friction mu s, take the reciprocal of that, the arc whose tangent, and that's an angle at which you cannot get the block to move if you push at that angle or something steeper. And that's problem number 1.